In the name of God, today we're going to address thermal conductivity under kinetic theory of gases. So similar to what we have addressed for deriving viscosity of gas, for the case of thermal conductivity, we're going to consider a molecule as kind of a thermal energy carrier. So if there is a source of thermal energy at some point of a system of gas, because the gases are moving randomly, then that thermal energy is going to be transported from the source point to some other parts of the gas system. So we begin by definition of heat as thermal energy in transit. So let me write this. Start with definition of heat. It's thermal energy in transit. Usually thermal energy get transported due to some difference in temperature, right? So thermal energy get transported from regions where the temperature is higher to regions where the temperature is lower relatively, right? So remember, we are considering non-equilibrium states of the gas system, but the system is in a steady state of whatever changes are happening. So for this to happen, we need this is due to temperature gradient. So wherever there is some difference in temperature, one can expect thermal energy to be transported. So let's see this in a schematic way. Supposing this is z-axis and the vertical axis is temperature. If we have some point T1 and another point with temperature T2, temperature T1 is at point Z1, and temperature T2 is at point, let's say, point Z2. Okay. So if supposing if T1, let's say, is greater than T2, then we expect that if there are some carriers of thermal energy, then this energy is going to be transported. Thermal energy from Z1 will be transported to Z2. Who is going to do that? The transport? The molecules. The molecules carry thermal energy with themselves, and they move around and distribute energy accordingly. So remember this last sentence, we can couple that with kinetic energy of the gas molecules, which we have derived earlier. So gas molecules energy, remember the average kinetic energy of a, let me write that as E, average kinetic energy. We have derived this to be 3/2 kBT times temperature using the Maxwell-Boltzmann distribution, right? So one can consider that on an average, a molecule of gas would have this energy depending on temperature, right? And as the molecules move around, we can think of them as carrying the energy with themselves around, right? And because of that, we can define kind of a heat capacity for a molecule, if that is C molecule. Remember, this is defined as change in energy with respect to the change in temperature. As we pump in energy, how does temperature increases? Okay, this rate of change of energy with respect to temperature defines heat capacity. Different systems would have different heat capacities. Different systems transfer energy at different rates, right? So we can consider molecules as such. And in this way, with the definition of average kinetic energy given above, one can consider dA, let's say, okay, I'll say average kinetic energy by dt. This is going to be a 3/2 times Boltzmann constant. Yep. So this is one part of the gist. I hope you've seen it. You're with me that molecules carry energy with themselves. As a result, they transfer energy from one point, let's say from Z1 to Z2. So with this, one can think of heat flow as some sort of flux, right? So let's say heat flowing from, let's say, point Z1 to point Z2 is some sort of heat flux. Heat flow can be considered as heat flux in the sense that molecules moving, let's say, per unit area, per time, will be carrying some energy crossing the area or cross-section under consideration, right? So with this definition, like heat flux, can write it as J, let's say it is J. Z, the subscript Z, is representing the direction of the flow. Let's say we're considering the direction as sketched above. This is usually defined as minus kappa, partial T, partial Z. Okay, or in 3D, one can write, let's say, the heat flux J vector is equal to minus kappa times the gradient of the temperature, the 3D gradient of temperature. Okay, so heat flux is heat flow per area per time, right? Definition of flux, we have discussed flux a lot of the time, and the constant kappa is what we call thermal conductivity. Thermal conductivity. So it's some constant that characterizes different sorts of materials or different sorts of gases. Different sorts of materials or gases will have different values of this constant depending on how effective or not they are in transporting energy from one point of the system to the other, right? As usual, we're considering a negative sign here. Also for heat flux, it's minus kappa, partial T, partial Z, because let's say as Z increases in this sketch, we can see that the temperature is actually falling down, so it's decreasing. Okay, so we bring in that minus sign to explicitly show the decrease in temperature with respect to the z direction. Okay, so in some way one can kind of think of the thermal conductivity, I hope, given like what we have mentioned so far, that thermal conductivity is going to somehow depend on like the heat capacity, right? Heat capacity of the molecules. Okay? Because heat capacity is what quantifies how energy changes with temperature. Okay, and here we're talking about heat flux and its change in temperature with respect to position. Okay, so let's go on to see how it's going, how this relationship between the thermal conductivity and heat capacity it's going to be like. Let's go to the next page. So I'll write this. Let's consider for let's write more clearly. For a molecule, we start as usual by considering a single molecule, and after having or deriving some expression of the change in temperature which that single molecule can like source, right? Then we can sum over all the different molecules within the system under consideration to kind of compute the total change in temperature due to, let's say, molecules crossing some constant z plane, some plane of reference, right? So for a molecule, crossing a constant z plane in the system, this single molecule would have traveled a distance lambda cos theta. So lambda is the mean free path of the gas, and theta is the direction at which the molecule under consideration is moving. So let's say the constant z plane is represented by this dashed line, and we have some molecule crossing that plane with some speed at an angle, with some velocity at an angle theta with respect to z, right? So since its last collision, the molecule would have traveled a distance of, on the average, the mean free path, and then the corresponding distance along the z direction is going to be lambda cos theta. So it would have traveled lambda cos theta and would have brought with itself, would have brought a change in temperature delta T. Okay, we can see delta T, supposing we know the rate of change of temperature, so partial T with respect to the z-axis, we just multiply this rate of change of temperature times the distance covered, by the molecule. Okay. So with this delta T, one can conclude that the corresponding thermal energy, brought by this single molecule, let's say that is going to be delta Q. Delta Q is going to be equal to the specific heat of the molecule. Remember, we defined specific heat of the molecule to be the change of energy with respect to time. So change of energy can be specific heat times change in temperature. Okay, and then substituting, this is going to be C molecule times partial T partial Z lambda cos theta. Okay. And with this picture, so we're talking of one molecule crossing some area, crossing some layer at constant Z per unit time, per unit area, and we can integrate over the velocities of the change in velocities and the different change in the directions to some for overall molecules, randomly crossing the area under consideration. That way we can compute the heat flux Jz is going to be integration from 0 to infinity dV and integration from 0 to pi times the change in thermal energy brought by a single particle, which is what we have discussed above. So I'm going to chuck it in. C molecule partial T partial Z lambda cos theta times all number of molecules, right, crossing the area per time, crossing the area under consideration. So that we have discussed, we have derived it. You can go back and look it again. V cos theta n of V dV is over there times 1 over 2 sine theta d theta, right? And doing the integration, you can see this is going to be equal to minus 1 over 3 NC molecule times the mean free path times the average speed of the gas times partial T partial Z, right? So comparing this with the definition of the heat flux Jx, we defined as minus kappa partial T partial Z, is then going to imply that the thermal conductivity is going to be equal to 1 over 3 NC molecule times mean free path times average speed of the system. So this is a very nice result. Okay, and this expression can be reduced to 1 over 3 CV times mean free path times average speed, where CV here is equal to the number density of the molecules times specific heat of a single molecule. Okay, and this is specific heat, definitely defined as heat capacity. So it's number density times heat capacity times heat capacity of molecule, right? So number density times heat capacity of molecule, it's going to be specific heat capacity. So how can I write that? It's called specific heat capacity. No, this is heat capacity per unit volume, right? So it's the number of molecules, total number of molecules divided by volume is going to be number density, and this is heat capacity of the gas molecules per unit volume. Okay, and the subscript V is actually describing how energy is changed with respect to temperature, but kind of keeping the volume of the system to be constant, right? This is the meaning of the subscript V here for the heat capacity per unit volume. Okay. And yeah, so that's a nice derivation from kinetic theory of gas for the heat capacity of gases. I mean, one can make substitutions, substituting the mean free path lambda, an expression for lambda, and then an expression for the average speed to kind of have. Let's write that. We can write the thermal conductivity as 1/3 heat capacity at unit volume times lambda average V. This is going to be equal to 2 divided by 3 pi d squared, bringing back C molecule kBT divided by pi m square root as the average speed of the molecule. Here we have used mean free path as 1/square root of 2 times n times sigma. Okay. And we've considered the cross-section sigma to be pi d squared, where d is on the average the diameter of the molecules. Right. Okay, so if you compare the thermal conductivity, the expression for the thermal conductivity and expression for viscosity, one can see that we can divide kappa, we can have kappa divided by eta, thermal conductivity divided by viscosity is going to be C molecule divided by m. Okay, and this is specific heat capacity. If we divide heat capacity of the molecule divided by mass of the molecule, this is defined as specific heat capacity. Okay, This is a nice relationship, even though it is simplified. There are some notes which we can mention, that the thermal conductivity of the gas system is really independent of pressure. See, in this expression we don't have pressure in it. It only depend on temperature. So thermal conductivity is directly proportional to temperature square root. And as before, for this system we have considered is such that we have the length scale of the container of the gas is much bigger than the mean free path, and the mean free path is much bigger than the diameter d of the molecules, right? Okay, this is one assumption. Another assumption is that we were considering like some area, some plane at constant z, and we were kind of considering that molecules crosses that layer equally over different velocities. So the molecules are going to have different velocities. It is true that there is an average. On the average, one can talk of the average velocity, but the individual molecules will have different velocity values, right? And in this derivation, like when we do the integration over here, we have actually assumed that all the molecules mentioned here are kind of crossing the particular layer under consideration at the same with the same probability, equally likely. But this is not really true because I'm not sure, we haven't addressed this, but considering like a unit area, it can be shown that molecules, actually it makes sense, we can see that molecules with with greater velocities are going to cross that particular area under consideration more often than particles with lesser speed values, right? So this is a simplification which we have used. So assumed that all molecules kind of cross the layer under consideration equally over different velocities. So with different velocity values, with different speed, but in reality, no, this is not the case. In reality, faster molecules cross more. Faster molecules will cross the layer more often than like the slower ones. So that's it for today. This is another very nice result from theory. So this is another showcase of theoretical physics, building things and then making predictions. Here, prediction is about, let's say, thermal conductivity. That's it for now. Catch you later. Goodbye for now.